Okay, so here we go. We are going to be starting back where we left off. We had made the concave up, concave down, the cowboy out of it. Oops, got a head. There we go. So that was where we left off. Now let's talk about something kind of cool. I'm going to erase that so it's not distracting me. Bye, little cowboy. So here we go. If I have f double prime of x greater than 0, it's concave up. If I have f double prime of x less than 0, it's concave down. What do I have when f double prime of x equals 0? Okay, so the way to think about this is to use the analogy that's in the f prime of x function. So if I think about it, when f prime, I'll even dash this over here, f prime of x is greater than 0, we have a slope that's heading up. When f prime of x is less than 0, we have a slope that's going down. And then if f prime of x equals 0, what do we have? Well, we have typically a transition between going up to down or down to up. So what does that look like? Well, for most things, it looks like it's going up, then it's heading down, but it's nice and smooth. It isn't a cusp. Okay? So that's one way, or it's going down and then it heads back up. And so we get these transition points where f prime of x is equal to 0 means you have a horizontal tangent, the slope is 0. But another way to look at it is really you are transitioning from going up to going down or going down to going up. That's really what happens at f prime of x equals 0. There's one other case which we'll kind of deal with here in a little bit, but that's the basic. Those are the basic things that can happen when f prime of x equals 0. So what happens when f double prime of x equals 0? Well, you have something very similar. You have a transition from going concave up to concave down or concave down to concave up. What does that look like? Well, it can look like something like this. Okay? This right here, this piece, so let me actually change color and kind of denote that. Let's see what color. Blue looks pretty good. So for this piece right here, we have concave up. Okay? Because you can imagine if I really wanted to, I could kind of extend this, and this is part of the bowl shape that I have right here. Okay? Then over here for the rest of it, so this piece, I'm going concave down, and it's kind of the same as this piece right here, right? So what happens at the middle? Well, at the middle, which is where I'm transitioning from concave up, greater than 0, to concave down, less than 0, this spot right here in the middle, that is f double prime of x equals 0. And that has a very special name. That is called oops, let me switch back to the normal color, and I'm not trying to talk about that. That is going to be what's called an inflection point. All an inflection point is where you have one type of concavity changing to another type of concavity. Okay? So concave up to concave down, or you could have the opposite, which would be something like maybe concave down to concave up, something like that. Where in this case right here, we're going to have this piece. Oh, I should do a different color. hold on, let me change color. This piece, if I can go over that, not too bad, corresponds to going to having concave down, this part of concave down, and then this piece right here corresponds to concave up. Something like that, right? And right here, in the middle, where we transition from one to the other, that is an inflection point. Alrighty? So, now, why are we focusing on this? Well, what we've been doing is graphing by hand functions that had cubics and some, I guess, rational expressions, things like that. And those graphs all were very simple. They did turnarounds and mins and maxes and humps and everything. Excuse me. So for those graphs, the first derivative was sufficient. However, it turns out there are tons of functions that you can't really get the behavior with just the first derivative test. You have to go to the second derivative and look at concavity. Now, luckily, almost all graphs can be handled with just the first and second derivative tests. But as you can probably imagine, as soon as we have the second derivative test, we have vastly increased the amount of time it takes to graph these things because we now have to find the second derivative. Second derivative is fine when it's a polynomial. Second derivative is not fun when you have some sort of rational expression, some fraction. So, since that is not fun, that's what we're going to do next. Let's do an example where we actually have to go through the f double prime of x process. So, here we go. This is an example of working through all these step by step. So, I'm going to clear the board and let's get started. So, clearing the board and let's get started. Okay, so for our first example, we're going to have a rational expression. So f of x is going to equal, we're going to have 6 over x squared plus 3. Okay? Now, I could do a rewrite with this to make it slightly easier to do the derivative, but I want a really messy second derivative so I can show you how bad it can get. So we're going to start off with this. And first things first, first step, we're going to look and see if this has any discontinuities. Are there any discontinuities with this expression? Well, no. There's no way I can get something that has to be positive, add 3 to it, and get 0. So any value I put in here is squared, which makes it positive. So positive plus positive is never 0. So there are no discontinuities with this one, at least for the original function. Alrighty. So second thing I want to do is find the critical numbers. So the critical numbers. And so part A, I'm going to look for, well, I need f prime, right? So f prime of x is going to be bottom x squared plus 3 times derivative of the top. Derivative of 6 is 0. Well, that's nice. Minus the top, 6, times derivative of the bottom, 2x. And all of that over the bottom squared. So x squared plus 3 quantity squared. What does that give me? That's going to give me negative 12x. Negative 12x over quantity x squared plus 3 quantity squared. Alrighty? So now that I have my first derivative, this is my f prime of x, are there any discontinuities? And absolutely not. I cannot get this equal to 0, so when I square it, it's still not equal to 0, so there are no discontinuities for critical numbers. So we're good there. There aren't going to be any cusps with this one. So part B, f prime of x equals 0. We want horizontal slopes, so I can, if I'm looking to set this piece equal to 0, when does that happen? Well, that happens when the top equals 0. So negative 12x equals 0, which means that x equals 0. Okay, so now that I have x equals 0, I go to the third step. And this time I actually have to tell you what table I'm going to be making, because I'm going to make the f prime table. And you can probably surmise from that we're going to be doing an f double prime table as well. So here we go. Let's make this table. It's not going to be too hard at all. So I have my x equals 0 critical number. I need a test value that is less than 0. So how about -1? X equals -1. And which function do I plug it in to make the f prime table? Well, of course, f prime is what I plug the -1 into. So when I do that, I'm going to get the bottom's always positive. The top is -12 times -1, positive. So positive over positive is positive, which means that this is going to be going up. We have an upward slope. So now I need a test value greater than 0. X equals +1. And f prime of +1, well, when I plug, bottom's still positive, I'll plug a 1 here. -12 times +1 is negative, so that is going to be a negative divided by a positive, which is negative, which means I'm going to have a downward slope for this interval here. So it's going up, then it's going down. That means that at x equals 0, I have what? Yep, I've got a max located right there. Alrighty, so now let's go to the next page. Let me clear this, and this is where it gets interesting. So let me clear this. I'm going to rewrite the f prime function down up at the top. So f prime of x is equal to -12x over quantity x squared plus 3 quantity squared. Alrighty, so here we go. That's my f prime. Now for the fourth step, I need to find the inflection points. Now I'll write it all the way out this first time. Okay, just like I had to find the critical numbers with my f prime, with my f double prime, I'm going to find inflection points. Okay, so first things first, I need to find f double prime. So this is a quotient, so here we go. It's going to be f double prime of x equals bottom x squared plus 3 quantity squared times derivative of the top, -12, minus the top, -12x, times derivative of the bottom, here we go, 2 times x squared plus 3 to the first power times the derivative of the interior, which is 2x. That's the chain rule that kicks in. We were using the power rule on something that wasn't plain old x, so we have to take the derivative of the interior piece. Now, all of this is over the bottom squared, x squared plus 3 to the fourth power. Okay? Now, this would be a horrible nightmare, except every single term has an x squared plus 3 factor in it. So I can now simplify this. So I'm going to take one of the factors away from each piece. And since this is just to the first power, this becomes a 1. Okay? Not to the first power like this one. This one went from the second power to the first power. This is, you know what, I'll make it even more visible by doing it this way. This becomes a 1. Okay? So, f double prime of x equals, we're going to have -12 times x squared, so -12x squared minus 36. And then over here, I'm going to have minus -12x, so it's positive 12x, times 2 is 24x, times 2x is 48x squared. So plus 48x squared and all of that is over x squared plus 3 now to the third power. I can simplify that because I have an x squared and an x squared, so this is going to become negative 12x squared plus 48x squared is 36x squared minus 36 over x squared plus 3 to the third. Alrighty, so now that I've got it into this form, all I have to worry about with this, I do not have to look for the critical number. Shoot, let me rephrase. I do not have to look at the first step of the critical numbers, which is looking for discontinuities. By the time you've reached here, you've found your discontinuities. There isn't a cusp of a cusp or anything like that. There are values that aren't valid that can pop up, but they are extremely rare, and they're really not all that common. Well, of course, extremely rare kind of includes that, but when I say they're not common, I mean, I have only seen them. I don't even know how rare they would be, where the f prime would still be continuous, but you would have some sort of discontinuity with your f double prime. I could see that if you start off with a function to the, gosh, what would that have to be? The 4/3 power, 5/3 power, something like that, which is just a very strange looking function. But I'm not going to ask you to check for discontinuities with f double prime. We're just going to skip that step and go straight to f double prime of x equals 0. So f double prime of x equals 0. Well, that implies that the top part equals 0. So 36x squared minus 36 equals 0. I can divide everything by a 36, and if I do that, that's going to become x squared minus 1 equals 0, which is x equals 1 and x equals negative 1. These are my two values when I solved. What are they? They are inflection points. So they are when f double prime equals 0. So inflection points. Okay? What is an inflection point? An inflection point is when you have a transition from concave up to concave down, or concave down to concave up. Okay? So we're now going to clear this and continue with our function. So clear that, and then now that we have our two inflection points, guess what we get to do? Yep, we get to make a table. So this time we're going to say that for step 5, we have make the f double prime table. And you could put of x in here if you want to, not needed. Okay, so I'm going to have a table here. X equals negative 1, x equals positive 1. I need my actual function up here, so I'm going to have f double prime of x equals, let's see, it was 36 x squared minus 36 over x squared plus 3 quantity cubed, something like that, right? Okay, so now that I have my double prime and I know what my inflection points are supposed to be, I need to know the behavior of either side of the inflection point. So I need a test value that is less than negative 1. How about negative 2? So f double, I'm sorry, let me erase that. We're not doing it that way. Up at the top, I just need to write the value. So x equals negative 2. F double prime of negative 2 equals, well, what am I going to get? If I plugged a negative 2 in, I would get 36 times negative 2 squared minus 36 over x squared plus 3, which is always positive, cubed, which is going to be positive. So this is just a positive value underneath. So what does this give me? This gives me positive 4 times 36 minus 36. That is definitely going to be a positive over a positive. So it is a positive. So positive, which means what is the behavior on this interval? It is concave up. Okay? So now that I've got that, I can move on to the next value, a value between -1 and 1. Yes, thank you. We are going to use x equals 1/8. No, we're going to use x equals 0, definitely. So f double prime of 0. Well, if I plug a 0 in right here, this term disappears. I'm left with -36 over something that's positive. Negative over positive is negative, which means it is going to be concave down. Okay, and then for the next one, I need a test value greater than 1, so x equals +2. Well, that doesn't change anything, does it? I'll get the same thing as I had over here because x's are being squared in both cases, so -2 squared is the same as +2 squared. So this is going to be positive, so f double prime of +2 is also positive, which means it's also concave up. Okay? So this is kind of something that I would expect to see. Where I have an inflection point, I better have a transition from one type of concavity to the other type of concavity. So I agree with all of this. Alrighty, last thing, y values. So we have to do this one last thing before we can graph it. So the y values, okay, I like to do them where I do the critical numbers first, and then I do my inflection point second. You can do them in numeric order, whatever you want to do. Totally fine. So for the critical numbers, I had f of 0, because that's where the critical number was located, right? So at x equals 0, what y value do I get? Well, I have to go back to my original function. My original function was f of x is equal to, I actually have to pull that back on the paper. I was going way past that. 6 over x squared plus 3. So 6 over x squared plus 3. So f of 0 is going to be 6 over 3, which is 2, which gives us the point at 0, 2. Okay? Now, for the inflection points, no, that doesn't really need that one doesn't exist. I'll just erase that. That never happened. Alrighty, so now that I'm looking for my inflection points, I'm going to do f of -1. So what does f of -1 look like? Well, 6 over -1 squared is 1, 4. So this is 6 over 4, which equals 3/2. So I'm going to get a value, -1, 3/2. And you can already probably tell f of -1 is going to be the same as f of +1 because they are squaring that value. So f of +1 is also 3/2. And I get something that looks like 1 3/2. Okay? So now I have all my values that I need to do, where they're located in space. I've got my critical number, which is the horizontal slope, and I believe that was a max. And then I've got my 2 inflection points, which is where the concavity changes. So now we're going to graph all this. Okay, so let me clear this and let's graph it. So let's see. I'm going to do a big old graph. Okay. Let's see. 1, 2, 1, 2, 1, 2. Okay. Now, this is something I like to do. You don't have to do it this way. It just helps me keep things straight. I had a max at 0, 2. So I like to denote horizontal slopes as solid circles and inflection points as open circles, just so it helps me figure out what the graph looks like. Okay. I then had an inflection point at 1 3/2. So there's an inflection point here. And there's an inflection point at -1 3/2. So right here as well. Okay. Now, I know that this is supposed to be going up. The slope, the overall slope is going up and then down, right? That's the two values I found on either side of my horizontal slope right here for my critical number. And now, what did it look like on either side of these inflection points? Well, the first one over here on this side of the inflection point, I had something that was concave up, and then between the two, I had something that was concave down, and then over here afterwards, I had something that was also concave up. And just by kind of labeling it, you can already see what this thing has to kind of look like. I have a max that is going to be coming down and then changing like that. Coming down and then changing like that. This is what the function looks like. This piece right here is always heading down. That's the slope. But this piece right here is concave down. This piece right here is concave up. Umbrella, bowl. Umbrella, bowl. And so that's exactly how the graph looks. Not too bad, right? Just a lot of extra steps. Now, once we do enough of these, you're going to be able to knock these out without too much trouble. But these take practice. So practice with the homeworks and everything else that I'm going to give you, and things will go a lot smoother for you down the road. Alrighty, so let's do another example. And this time we're going to have some very strange behavior. Okay, so let me clear this, and then we will jump on to the last example. Okay, so the next example is going to be a much easier one to differentiate, but it's going to be a little strange when we're doing it. So f of x is going to equal x to the fourth minus 4x cubed. Okay? First off, step one, does this have any discontinuities? Absolutely not, because it is a polynomial, so no discontinuities. Step two, we need to find the critical numbers. Okay? So the critical numbers, well, for that I need f prime. So f prime of x is going to equal 4x cubed minus 12x squared. Okay? Part A, are there any discontinuities for cusps? Nope, no discontinuities. But we do have f prime of x equals 0. That implies that 4x cubed minus 12x squared is equal to 0. And I can factor out a 4x squared and be left with x minus 3 equals 0. And that means that x equals 0 and x equals 3 are our two critical numbers. So now that we have those, let's make the f prime table. So make the f prime table. So I'll put that one over here. We're going to have x equals 0 and x equals 3. Alrighty. I need a test value less than 0, so maybe x equals negative 1. So if x is equal to negative 1, I wind up with f prime of negative 1 equal to, well, let's see. Negative 1 cubed is negative 1 times negative 4, times 4 rather, is negative 4, minus, I'm going to have a positive value here, so positive 1. 12 times positive 1 is positive 12, so negative 4 minus 12 is negative, so I have the slope going down. Okay? Now, a test value between 0 and 3. How about x equals positive 1? Okay, if x equals positive 1, I'm going to have positive 4 minus 12. So f prime of positive 1 is also negative. Okay, you see the oddness here, the problem we have? On this interval, the slope is down. And on the next interval, it's still down. But we have a critical number here. Okay? This is going to be the very first example of where we have a horizontal slope, which is what f prime of x equals 0. That's what this value is. It's a horizontal slope. That is not a min or a max. So we'll get to it. We'll figure it out. So let's come on over here. Let's finally do a test value greater than 3. How about x equals 10? That's a nice one. X equals 10, I get 4,000 minus 1,200. And so the 4,000 definitely dominates. That is positive. So f prime of 10 is equal to positive, which means it's going up. Alrighty? So right here at x equals 0, I don't know what it is. It's not a min or a max, but it's some sort of horizontal slope. But right here at x equals 3, I have it going down, then back up. That is going to be a min. So that one I can identify. All right. Now, step 4, let's do inflection points. So let me clear this. So step 4, we're going to find the inflection points. So how do I do that? Well, I need f double prime of x. Well, f double prime of x is going to equal the derivative of the f prime, which is going to be 12x squared minus 24x. Okay? So I told you don't really have to worry about the discontinuities at this point, but we do need to see where f double prime of x equals 0. That's where we have our inflection points, the transition from one type of concavity to the other. So how do I find that? Well, I'll set this equal to 0 and solve. So 12x squared minus 24x equals 0. I can factor out the 12x. If I do that, I'm left with x minus 2 equals 0. So x equals 0 and x equals 2. Okay? Aha! I have the same location that I had for the critical number, x equals 0. This is the one that we found that wasn't a max, wasn't a min. It was a horizontal slope, but that's all we could tell. We also now know that it is an inflection point, a change in concavity at this point. So now let's make the f double prime table. Okay? So here we go. I'm going to have one inflection point at x equals 0 and another inflection point at x equals 2. Okay? So I need a test value that is less than 0. How about negative 1? Doing f, not f, that's just x. X equals negative 1. What do I plug it into? Well, it's the f double prime table, so I'm probably plugging it into f double prime. So f double prime of negative 1 equals, well, what would we have? This is going to be squared, so it's positive. 12 times positive 1 is 12. And then negative 1 times negative 24 is positive, so positive and a positive, it is positive. So this one is going to be concave up. Okay? Now, over here, I need a value between 0 and 2. How about x equals positive 1? F double prime of positive 1 is going to equal, well, 12 minus 24 is negative, so I'm going to get concave down. Okay? Last but not least, a test value greater than 2, maybe x equals 10. So I'm going to get 1200 minus 240, definitely positive. So f double prime of 10 is positive, which means concave up. Okay? Whew. So I have a lot of information, and I'm now going to go to the f values. So I'm going to clear this and figure out what all the y values are, rather, for my function. So I'm going to clear this, and this is going to be step 6, the y values. And as I said before, I'm going to do the critical numbers first, just because I like to keep everything kind of straight. And what were the critical numbers? Well, I had f at x equals 0. That was one of them. And so if I look at my original function, let's see, the original function, I don't have space right here, so let me erase this. There, it's all erased, gone away. My original function was f of x equals, I had x to the fourth minus 4x cubed. Okay, so critical numbers. I had one at x equals 0, so at x equals 0, I get f of 0, where it says located in the y, 0 minus 0, that is 0. So I get a value at 0, 0, the origin. The other critical number was at x equals 3. So f of 3 gives me the y value of 3 to the fourth is 81 minus 4 times 27, which is negative 108. So negative 108 plus 81 is going to be negative 27. So this is going to be located at 3, negative 27. Okay? And this is some sort of min, so I'm not surprised that it's super negative. Alrighty, now I'm going to find my inflection point, y values. So at x equals 0, well, I already have that, right? I know what the y value is for that position. It's at 0, 0. Okay? But I also had x equals 2. And so x equals 2 gives me, oh well, f of 2, which is 2 to the fourth is 16 minus, this is going to be 8 times 4 is 32. 16 minus 32, it's going to be negative 16. And so that point is located at 2, negative 16. Okay? So now that I have all these values, I can now graph the function. Okay, so let me clear this and let's sketch a graph. Here we go. A lot of information to put down. So first things first, I'm going to just kind of remind myself what I had. I'm going to look back at the f prime table. So the f prime table, it's just so we can have all the information in one place. I had x equals 0 and x equals 3, and I had down, down, up, and the f double prime table, I had at x equals 0 and x equals 2, which I'll put somewhere around here. Okay, what did I have? Well, I had concave up, concave down, concave up. Okay, what were the points? What were their y values? Well, I had that for this x equals 0, it occurred at 0, 0. And then this value was at 3, negative 27. Again, this is at 0, 0. And this value was at 2, negative 16. So 2, negative 16. Alrighty? So I'm going to graph this with kind of an emphasis on the negative values. So something that looks like this maybe. Alrighty? I'm going to go 1, 2, 3, and I'll do negative 16 here and negative 27 here. Okay, so let me label my points. I have, this is where it gets a little bit odd, a critical number and an inflection point at the same value, so it's kind of like a dot, and then there's also an inflection point there. That's odd. And then I've got the second solid dot at 3, negative 27, so down here. And then at 2, negative 16, right here, I have an inflection point. Okay, what does the graph have to look like? Well, it has to be heading down here. And then between this value and this value, it's still heading down. So it's still heading down. And then it heads up after x equals 3. Okay? But what does the concavity look like? Well, this is concave up on this piece, so something like that. This is concave down from here to here, so this is concave down, and then this is concave up from this point on, something like this. Okay, now let's sketch the actual graph, and I'm going to use purple. So here's what this has to look like. The only way I get an inflection point and a critical number at the same location is to have a horizontal slope in which the concavity changes. So the only way I get that is if I get something that looks like these two situations. So I either have this, or I have, let's see how to do this other one, this, where right here the concavity changes from up to down or from down to up, and there's a horizontal slope right there. So this is what happens when it's not a min or a max, but it is a horizontal slope. It has to be a point of concavity. An inflection point at that point, a point where the concavity changes. That is the only way you get a horizontal slope without having a min or a max. So with that in mind, that's what this has to be. And which one does it need to be? Well, it's concave up, then concave down, which means it's this one. So it does something like that. So this is a horizontal slope. It's also transitioning from concave up to concave down. This is a point where it's transitioning from concave down to concave up. And this down here is a min. And so that is how you graph this function all at once. What do you think? That's a lot, isn't it? So if you ever have a critical number and an inflection point at the same value, it is one of these. It's a horizontal slope at an inflection point, which looks just like this. Then the rest of it is just filling in the pieces. But you can already see this would have been impossible to graph without this the second derivative, the f double prime test. So that's why we have to have it. When you get a more complicated function, you're going to wind up with things that require at least the second derivative to graph. Alrighty? So that is everything for the initial jump into this section. I'm going to give you some homework, if you will. So this is going to be from 3.4. This is going to be the second homework. The first homework from this section. Second video, first homework. And the homework, if you will, tackle number 6 and number 10. Okay? And then we will pick up with that homework. And the homeworks are going to look similar to what we've done. And then we'll move into more complicated examples for part 3 of concavity. All right, that's all it is for this video. Have fun graphing this, and I will see you in a little bit. Bye-bye.